Hello viewers, welcome back to the course on matrix computation and its application. So, today we are continuing from the definition of vector spaces, and today we will discuss with the another definition, that is subspaces. So, what is the subspaces? So, in the previous lecture we have seen that suppose this is my some vector space V. So, now what we are going to define in the vector space, all the properties are satisfying: vector addition, scalar multiplication. Now, we want to see that what will happen if I have some subset. So, suppose I take the subset S. So, S is a subset of V. Now, I want to see what is going to happen with this set S. So, let us define the definition subspaces. Let S be a non-empty subset of the vector space Vf. So, in this case we are taking the vector space V, and F we know that it is defined over the field F, and S is a subset of V. So, it is a proper subset or maybe equal to V also. So, that is why this equality sign is there. Now, if S is also a vector space over the same field F. So, same field we are taking using the same vector addition and scalar multiplication, that you have to keep in mind, that if S is also a vector space over the same field with the same vector addition and scalar multiplication, then S is called to be a subspace of V. So, then S is also a vector space itself under the same operation, and then S is called the subspace of V. Now, the question is that if we have to check that S is a vector space or no, then whether we need to satisfy all the properties, what all the 8 properties we have satisfied in the case of vector spaces. So, then it becomes that it is not necessary to check all the definition or on the defining condition in order to check if a subset is also a subspace. So, what we need to do? We need to check only 2 property. The closure property needs to be considered. It means that we need to check only the vector addition. So, this is if I take 2 elements, 1 element and 1 element, and I take 2 elements from S and I define the same vector addition, what we have defined belongs to S, then it is the vector addition, and if it is belong to the same S, then this property is satisfying, and this one is the scalar multiplication. So, if I take U belongs to S and any scalar alpha from the field, and then if I define this one scalar multiplication, and that also satisfy in the set S for all alpha, then this I can say that the scalar multiplication is well defined for S also. Similarly, the vector addition is well defined for S also, and then if these 2 properties are satisfying, then we say that S is a subspace of vector space V under the same operation. So, it is a subspace of V. Now, let us start with the simplest subspace. So, the simplest subspace, let if S is equal to 0 element. So, this is a 0 vector we are taking, then it is called the trivial subspace, and all the other subspace of V are called non-trivial subspaces of V. Okay. So, how I want to verify that how this is a trivial subspace, because it contains only one element, S is equal to 0, and this 0 is a additive identity. So, that is a 0 element basically we are taking. Now, you can check that it is a subspace. So, 0 plus 0 is 0. So, that belongs to S. So, vector addition is there. Now, if I take any scalar alpha into 0, then we have satisfying this property that for any alpha into the 0 vector, that is again 0, and that belongs to S. So, vector addition is well defined, scalar multiplication is well defined, and just now we have seen that if these two properties are well defined, then it is a subspace. So, from here we can say that S is a subspace of vector space V with the field F, and only one element is there, that is a 0 element. So, I can say that this is the only subspace having finite number of elements, because if you take any other subspace, then it is will be called non-trivial and it is going to have infinite number of elements. So, only this subspace is the only subspace which contains only one element or a finite element, and that is the trivial subspace. So, this is just the definition of the trivial subspace. Now, the next thing is that how we can check that whether it is a subspace or not. So, I just want to give one property that the subspace must contain the 0 element of the vector space V. 0 element means additive identity, it always contain this one. If it is not contained, then that is not the subspace of that vector. So, let us define some examples. So, let us take one example. Suppose I take a vector space V, and let us take V is equal to V2, that is basically R square. So, it is I know that this is a set of all x y elements where x and y belongs to the real number. So, that is defined and we know that it is a vector space. Now, I take a set S and I choose the set S, only x is there and other element I just make 0 where x belongs to the real number. Now, the question is that I know that this S is a subset of V2, because I am just substituting one element equal to 0, that is it. Now, definitely it is a subset of V2. Now, from here I want to check. So, we want to check S as subspace or not. So, this one I want to discuss. Now, I am taking the subspace from V2. So, in V2 we know that we have defined the vector addition as usual addition and scalar multiplication. So, I am going to do the same same vector addition and scalar multiplication. Then let us satisfy that let I take U and V belongs to S. So, suppose U is basically I am taking x1 0 and V I am taking x2 0. So, this belongs to S and this belongs to S. Now, I define U plus V. So, u plus v is I am defining x 1 0 plus x 2 0. So, this is going to be x 1 plus x 2 0 by the usual addition in this case, and from here I can define that this is also belongs to S, because it should be some real number and this should be 0. So, that belongs to S. So, it is means addition is well defined. So, satisfied. So, first property is satisfying. Second one is alpha into u. So, alpha and u I am taking x 1 0. So, from here I will now define the scalar multiplication. So, this will be equal to alpha x 1 and alpha 0, and alpha 0 will be 0. So, it is alpha x 1 0, and that also belongs to S. So, if it also belongs to S, then this is also satisfied. So, from here I can say that S under the same binary operation and is, or I can, we generally we have to write like this one, because it is a subspace. So, we should write that S is a subspace of V under the same operations, or I can say that S is a subspace of V. So, it is a one subspace we have discussed. We can have many subspaces. So, that we do not know that how many subspaces it can have, but it can have many subspaces, and so in that case I am just showing that one set I have chosen is a subspace of V. And from here you can also see that 0 0 element is also belongs to this, that also belongs to S. So, I told you earlier also that 0 0 element should belongs to S. That is also one of the quick way to check whether the given set is a subspace or not. If the 0 element is not there, then you just certainly can say that it is not a subspace. For example, I take another example. I just choose the another example as the same way. I just take x here, and another element I just take 1. Okay. And from here x belongs to R. So, I know that this is also a subset of V 2. V 2 I have defined. So, it is a subset of V 2. Now, from here I want to check whether it is a subspace or not. So, in this case, since I can write, since 0 element, that is 0 0, does not belong to S. So, from here I can say that S is not a subspace of V. So, directly I can say from here that this is not a subspace of V. Similarly, I can define another subspaces, many subspaces. So, let I take another example. So, in the another example I just take V 3 over the field F with visual addition and scalar multiplication. I know that this is a vector space. So, I take S is equal to, maybe I can take x 0 and minus 1, this element, and that belongs to x belongs to real number. So, it is a subset of V 3. Now, again 0 0 0 element does not belongs to S. So, which implies that S is not a subspace of V3. So, directly we can write that it is not a subspace of V3. Now, let us take few more example. I have defined the P and X. Okay. So, P and X I have defined under the addition, usual addition or scalar multiplication, that is a vector space. So, it is P n, I know that this is a set of all polynomial of degree less than equal to n, and x belongs to my interval I. So, this one we have defined. Now, I take a set S. So, this set I am taking so that I can define set of all polynomials of degree less than equal to n such that P n x 0 is equal to 0, where x 0 belongs to my I. It means I am taking all the set of polynomials of degree less than equal to n, in which x naught is the root of that polynomial. So, definitely it is a subset of P n x. Only thing is that it should be the root, it contains all the polynomial whose root is x naught. Now, from here you can check that it is a subspace or not. So, from here I can take, so let we take P 1 and P 2 belongs to S. Then if it is belongs to S, then P 1 x naught is 0 and P 2 x naught is also 0, right. So, what I will do, P 1 plus P 2, this one I want to check. So, let us check what is happening at x naught. So, this is equal to P 1 x naught plus P 2 x naught, and this is 0 plus 0, and that is equal to 0. Okay. So, this is true for P 1 and P 2, and it means that is also belongs to S, because in this case P 1 plus P 2, that is a polynomial that is also having x naught as a root. If it is having a x naught as a root, then it belongs to S, because definitely the degree of P 1 plus P 2 is always less than equal to n. So, this will belong to S. So, the first one is satisfied, and the second one is I am defining that P 1, the polynomial I am taking, and multiplying by cell alpha. So, let us see what will happen at x naught. So, definitely it is equal to P 1 x naught, and this is again it is going to be 0, because alpha is just multiplying, I can take it outside, and P x naught is 0. So, I can write alpha into x naught, and alpha into 0 is 0. So, that is equal to 0, it means that is also belongs to S. So, vector addition and scalar multiplication is defined for the set S. So, from here I can say that S is a subspace of vector space P and X. So, this is I just take and I found that this is a subspace of P and X. So, in this example this is making the subspace. Let us take another example. Now, in this case also I just here I want to check whether 0 element is there or not. So, if you see that if I take a 0 polynomial and x naught So, it is always 0, it means it belongs to S. So, from here I can say that 0 polynomial also belongs to S. Now, let us take another set S. So, in this case also I am taking the set of all polynomial of degree less than equal to n such that P n at some element A is equal to 1. So, where A belongs to the given interval, this one. So, definitely it is a subset of P n x. Now, I am taking those polynomial in which I put the value of A, some A element is there in that given interval, and it gives the value equal to 1. Now, I want to check whether it is a subspace or not. So, the main question is that I told you that first you can check about the 0 polynomial. So, let us check zero polynomial. So, I know that the 0 polynomial is the polynomial whose all coefficients are 0, and it is a 0 polynomial. So, that is I am taking and I am finding its value at A. Okay. So, 0 polynomial means this one 0 x n, 0 x n minus 1, 0 x n minus 2, 0 x 0, that is it. So, this is my 0 polynomial, and if I take 0 A, I am putting the value A here. So, it will be 0 into A power n, 0 A power n minus 1 up to 0, and that will be 0. But if I take a polynomial and substitute value A, then it should come 1. It means it does not belongs to S. So, from here I can say that S is not a subspace of P n x. I can say from here that this is not a subspace of P n x. Okay, so, this way we can define the subspace. Now, so after taking few examples of the subspaces, I can just define one more term, that is we call it linear combination. So, this term is the linear combination means that let V is the vector space. Okay. And I choose some elements V1, V2 to Vn. So, I am defining n number of vectors belongs to V. So, V is a vector space and I choosing n number of vectors out of that, and let us define their combination scalar. So, I just define alpha 1 V1 plus alpha 2 V2 alpha n Vn. So, this if we take this one, then this is called linear combination of vectors V1, V2 up to Vn. So, this is called the linear combination, where alpha 1, alpha 2 up to alpha n, that belongs to the given field F. Okay, so, this is called the linear combination. So, from here I give you the definition of linearly independent or dependent vectors. Okay. Now, the set, suppose S is a set V1, V2 up to Vn, that S is a set of vectors where Vi belongs to the given vector space V. So, vectors V is a vector space. Some vector space there, and I am choosing Vi some vectors from out of these. Then the vectors V1, V2, Vn, the set of vector. So, these vectors are called linearly independent if I take the linear combination alpha 1 V1 plus alpha 2 V2 up to alpha n Vn. Now, you see that V1, V2, Vn I am taking from V, and which is a vector space, and alpha 1, alpha 2 I am taking the scalar multiplication. So, this is well defined in this case, because it is a vector space. Okay. And now, it is a vector space. So, 0 element definitely will be there. So, I am putting this equal to 0. So, if I take this linear combination equal to 0, okay. So, and this, so these vectors V1, V2 up to Vn are called linearly independent. If this is equal to 0, implies alpha 1, alpha 2, alpha n all are 0, or I can just make it little bit elaborate. Then alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to alpha n, all are 0. Okay. So, all are 0. So, in this case 0 means the scalar are 0, and this is a 0. So, it means 0 vector I am defining belongs to the given vector space V. Otherwise, it is called linearly dependent. Otherwise, we will call it the linearly dependent. If all the coefficients are coming 0, then it is linearly independent, and otherwise if any one of them is non-zero, then just we can say that this is linearly dependent. Now, we define the next definition, and that definition is span of S. So, this one I want to define. Okay. So, what is that? For a set of vectors, I define a set S as vectors V1, V2 up to Vn. So, this is I am just taking a set of vectors where V1, V2 or Vn belongs to the vector space V. Okay. So, this is a vector space. for a set of vector this from a vector space V over the field F, the set of all possible linear combinations of the vectors means VI's, what I am taking would take, is denoted by, so I am just defining, I am taking all alpha 1 V 1 plus alpha 2 V 2 plus alpha n V n, okay, where this alpha i's belongs to the field F. So, this I can take all the combinations, whatever the combination there, I can change my alpha i's and then different type of combination I can get. So, then these combinations are called span of S, and this is represented by S and close bracket, square bracket. It means that I am taking this S is this set. So, of this set I am taking all the possible linear combination, and whatever the linear combination I will take then I will get another set, and that set is called the span of S. Okay, so, this span is represented by this one. So, after this let me stop here. So, today we have discussed about that what do you mean by the subspaces, and then we have discussed few example based on the subspaces, and then we have defined another definition, that is span of S. So, in the next lecture we will continue with this one. Thanks for watching, thanks very much.